you think the universe has an edge. Maybe you haven't said it in those words. Maybe you've heard that space is infinite and nodded along. But somewhere underneath that nod, your brain is doing something it cannot stop doing. It is imagining a boundary, a place where the stars thin out, a region where the galaxies become sparse, and then absent, and then there is nothing, and then, just past that nothing, something else. Something that the universe is expanding into. Some kind of outside. Your brain is doing this because it is a brain. Because every brain that has ever existed developed inside a world of bounded spaces. Rooms have walls. Continents have coastlines. The atmosphere has an edge where it dissolves into space. Your skin is the edge of your body. Every physical space you have ever occupied or imagined has had a boundary. An inside and an outside. A here and a there. And so when you hear that the universe is the largest structure in existence, that it contains everything, literally everything, including every place and every object and every region of space, your brain accepts this intellectually and immediately starts building an edge around it anyway. Because a container without walls isn't something you have any experience of. It doesn't correspond to anything in your life. Your brain fills in the gap with a wall. This isn't a failure of intelligence. It is the correct function of a mind built for the world it actually lives in. For the vast majority of human history, and for the entirety of evolutionary history before that, the ability to model boundaries was one of the most important cognitive functions an animal could have. Where does this territory end? Where does the cliff begin? Where is the edge of the ice? Minds that modeled boundaries survived. Minds that didn't. You are the descendant of millions of years of creatures that were very, very good at finding edges. And now, you are being asked to comprehend a space that may have no edge. The same cognitive machinery that kept your ancestors alive is the machinery you're trying to use to understand the geometry of the cosmos. It was built for one job. The cosmos is presenting it with a completely different job, one for which evolution provided no preparation. The difficulty you feel when you try to picture the universe having no edge is not a sign that you're thinking about it wrong. It is the accurate sensation of a mind encountering something outside the domain it was designed for. You are feeling, in real time, the limits of the cognitive architecture that makes human thought possible. Here is the thing that nobody explains clearly enough. The universe may not have an edge. Not in the sense of a wall you haven't reached yet. Not in the sense of a place where space stops and something else begins. Not a border. Not a surface. Not a region where the galaxies end and the void begins. No edge. At all. Not because scientists haven't found it yet. Not because it's very far away. But because the geometry of the universe, as best we can measure it, is consistent with a space that doesn't end. That has no boundary in any direction. That is, in the specific mathematical and physical sense that matters here, infinite. And if that's true, if the universe really has no edge, then the question of what's beyond the edge doesn't just lack an answer, it lacks a subject. There is no beyond the edge to ask about. The question is asking about a thing that doesn't exist, and that realization doesn't make things simpler. It makes things stranger. Because an infinite universe has consequences that are, in their own way, more disturbing than any wall could be. There's an important difference between saying the universe is very big and saying the universe may be infinite. The first is easy to process, in the way that a billion is easy to say while being impossible to truly feel. Very big is just a large version of the sizes you already know. Infinite is categorically different. It's not a large number. It's not any number. It is a property of a space that has no end. Not just a very distant end. Not just an end that requires a very long journey. But no end. Never. In any direction. Forever. In part 1 of this journey, we're going to dismantle the wall your brain keeps building. We're going to go through what the measurements actually say about the shape and size of the universe. We're going to confront what infinite actually means, in its real mathematical consequences, not just as a comforting word. And we're going to arrive at the specific, real boundary that does exist, not the edge of the universe, which doesn't appear to be there, but the edge of what you can ever reach. The edge of what can ever reach you. That edge exists. It's not where you think it is. It's moving in the wrong direction, and what it means for the future is genuinely, quietly terrifying. Before we get started, If you love exploring the depths of space and the great unanswered questions of the cosmos as much as we do here, take a moment to like this video or subscribe to the channel. It helps more curious minds find their way here and keeps this journey going. Now, let's actually look at what's out there. When someone asks, what's beyond the edge of the universe? There are two completely different questions hiding inside that question, and they have completely different answers. The first question is, what's beyond the observable universe? What's outside the sphere of space from which light has had time to reach us since the Big Bang? This question has a real answer. Beyond the observable universe, there is almost certainly more universe, more galaxies, more stars, more space. The observable universe, the sphere of everything we can see, is not the universe. It's the part of the universe we can access with our instruments right now, defined by the speed of light and the age of the cosmos. Something can exist beyond that boundary, without violating any law of physics. It's just further away than light has had time to travel. The second question is, what's beyond the universe itself? Not just beyond what we can see, beyond all of space. What is space inside of? What surrounds it? What's outside the totality of everything that exists? This question is much harder. And the answer, depending on what the universe's geometry turns out to be, may be that the question contains an assumption that doesn't apply. That outside the universe is like north of the North Pole, not just difficult to describe, not just very far away, literally without meaning. Tonight, we're going to address both questions, starting with the one we can actually measure something about. The universe is 13.8 billion years old. Light travels at 300,000 kilometers per second. In 13.8 billion years, light can travel 13.8 billion light years. So you might expect the observable universe, the sphere of everything we can see, to have a radius of 13.8 billion light years. It doesn't. Its radius is about 46 billion light years. This is the first thing that trips people up. How can the most distant light we can detect have come from a place that is now 46 billion light years away? If the universe is only 13.8 billion years old, and light travels at a fixed speed, the answer is the expansion of space. When that light left its source, the source was much closer to us than 46 billion light years. The light has been traveling toward us for 13.8 billion years, but while it was traveling, the space it was crossing was expanding. By the time the light arrived, the source had been carried to a distance of 46 billion light years by the expansion. This is not a technicality. It is fundamental to understanding what the observable universe actually is. The observable universe is a sphere with us at its center, radius 46 billion light years, containing everything from which light has had time to reach us since the beginning. Right now, if you could see the full extent of it, it would contain roughly 2 trillion galaxies, each galaxy containing hundreds of billions of stars, each star potentially hosting planets. The scale is genuinely beyond what the human mind can hold. And it's only a fraction of what exists. Here's how we know. Look out in any direction, and the universe looks the same. The same density of galaxies. The same distribution of matter. The same cosmic structure. The same physical laws. There is no direction you can point a telescope that shows you the universe thinning out, the galaxies becoming sparse, the density dropping towards some natural boundary. In every direction, all the way to the limit of what we can see, the universe looks like more of the same. The observable universe ends not because the universe ends, but because light hasn't had time to arrive from further away. It's a visibility limit, not a boundary of existence. Past the edge of the observable universe, there is almost certainly more universe. The same kind of space, with the same kind of galaxies, extending in every direction. How far does it extend? This is where the question of the universe's geometry becomes unavoidable. Whether the universe is finite or infinite depends on its geometry. And the geometry of the universe is a measurable physical quantity. In general relativity, Einstein's theory of gravity, the most precisely tested physical theory we have, space-time has curvature. The presence of mass and energy curves the fabric of space-time, producing what we experience as gravity. At the largest scales, the distribution of all the mass and energy in the universe determines the overall geometry of space. There are 3 broad possibilities. First, Positive curvature, like the surface of a sphere, but in 3 dimensions. In a positively curved space, traveling far enough in any direction eventually brings you back to where you started. The space is finite, but has no boundary. No edge, no wall, no outside, but a finite total volume. 2 parallel lines extended far enough eventually converge. A triangle's angles add up to more than 180 degrees. Second, negative curvature, like the surface of a saddle, but in 3 dimensions. Space curves away from itself in every direction. Parallel lines diverge. A triangle's angles add up to less than 180 degrees. This space is infinite, extending forever, never closing back on itself. Third, flat. The geometry of ordinary Euclidean space. Parallel lines stay parallel forever. A triangle's angles add up to exactly 180 degrees. Space extends in all directions without limit. This space, too, is infinite. These 3 options have very different implications for the question of what's beyond the edge. In a positively curved, finite universe, there is no edge. There is no beyond. You can travel in any direction indefinitely and never hit a wall. You'd eventually return to your starting point, like an ant traveling on the surface of a sphere. The universe is inside itself, in a sense. Asking what's outside it is like asking what's outside the surface of a sphere. The surface has no inside or outside. Those concepts don't apply to the surface itself. In a negatively curved or flat universe, there is also no edge. The space extends infinitely. There is no wall to run into. There is no beyond, because there is no limit. The universe doesn't end. It just keeps going. In none of the 3 cases is there a wall, a border, a surface that marks the edge of space with something else on the other side. So which one is our universe? The most precise measurements we have, from the Planck satellite's mapping of the cosmic microwave background, are consistent with a flat universe. Not approximately flat. Flat to within the measurement uncertainty of the best instrument we have ever built. The universe's curvature, the parameter that would deviate from 0 for a positively or negatively curved space, is consistent with 0. A flat universe is infinite. The most likely geometry of our universe is infinite space extending in all directions forever, with no edge and no outside. Most people, when they hear the universe is infinite, process that as the universe is very large. Their brain substitutes very large for infinite, because very large is something their experience can almost approach, while infinite has no experiential equivalent at all. Here is what infinite actually means. In an infinite universe with the same physics throughout, the same laws, the same constants, the same distribution of matter, any finite region of space will be repeated somewhere else, not similar. Not approximately the same, exactly the same, in every detail. This follows from the mathematics of infinity combined with the finiteness of possible configurations of matter. The observable universe has a finite volume and contains a finite amount of matter. That matter is arranged in a specific configuration, every particle in a specific place with a specific velocity. The number of distinct configurations of all the particles in the observable universe is astronomically large, but it is finite. Any finite number, no matter how large, is infinitely smaller than infinity. In an infinite universe, every finite configuration must occur, not probably occur, must occur. Infinity divided by any finite number is still infinity. There are infinitely many regions of the universe, the size of our observable bubble. Each one contains a specific configuration of matter. Because the number of possible configurations is finite, and the number of regions is infinite, every configuration must appear infinitely many times, including this one, right now, at a distance of approximately 10 to the power 10 to the power 28 meters from where you are. A number so large that writing it out would require more digits than there are atoms in the observable universe. There is a region of space that is an exact duplicate of the observable universe, with a duplicate Earth, a duplicate solar system, a duplicate Milky Way, a duplicate you, in the same room, in the same position, listening to the same thing. This is not a metaphor. It is not a philosophical speculation. It is a direct mathematical consequence of an infinite flat universe with a finite number of possible matter configurations. If the universe is infinite, there are infinitely many copies of you. Right now. having exactly this experience. Some of them will make slightly different choices tomorrow. Some of them are living your life forward differently, starting from the identical moment you're in now. Some of them will have experiences that diverge from yours gradually, over years, in ways neither of you could predict. This is either the most comforting or the most disturbing fact about the universe you have ever encountered. There is no right emotional response to it. Both comfort and disturbance are appropriate. What I can tell you is that it follows from the math, not from speculation, from the mathematics of what infinite means. And the measurements say the universe is flat. There is a boundary in the universe. Not a wall, not a physical surface, but a boundary that is real, that has a specific location, and that you cannot cross. It's called the cosmic event horizon. At a distance of approximately 16 billion light-years from us, there is a sphere beyond which the expansion of space is so fast that nothing, no signal, no photon, no information, can ever reach us from the other side. The space between us and any object beyond this horizon is expanding faster than light can cross it. Light emitted by those objects today will never reach us, no matter how long we wait. This is not because of any physical barrier. There is no wall at 16 billion light-years. If you could somehow teleport to that distance, there would be nothing special about that location. Space looks the same. Galaxies are present. The laws of physics apply normally. There is no sign you're at any kind of edge. But from our perspective, here in this specific location, any light emitted from beyond that horizon today is running a race against the expansion of space and losing. The space it's trying to cross is growing faster than it can travel. That light will never arrive. This is the real edge of the reachable universe. Not a wall, a velocity boundary. A limit defined not by the absence of space, but by the speed at which space is growing. And here is the thing that makes this genuinely disturbing. The cosmic event horizon is not fixed. It is moving. And it is moving in the wrong direction. Because dark energy is accelerating the expansion of the universe, pushing galaxies apart faster and faster. More and more of the universe is being carried beyond the horizon every day. Galaxies that were inside our reachable universe yesterday are outside it today. Their future light can no longer reach us. Right now, as you listen to this, galaxies are crossing the event horizon. Not one, not 10, millions of them, continuously, at a rate that is increasing as the expansion accelerates. Every galaxy that crosses the horizon is lost to us forever. Not temporarily, not until some future technology can retrieve the signal. Lost. The information from those galaxies, any message they could send, any light they could emit, will never arrive. In approximately 150 billion years, roughly 10 times the current age of the universe, every galaxy outside our local group will have crossed the horizon. The night sky of that far future will contain only the merged remnants of the Milky Way, Andromeda, and the few dozen dwarf galaxies bound to them. Everything else will be gone from observational reach. If astronomers exist in that era and have no record of the universe we can see today, they will look out at the sky and see only their local island. They will have no evidence that anything else exists. They might conclude the universe contains only their galaxy, with no way to know how much they're missing. We are, by an extraordinary coincidence of timing, alive in the epoch when the universe's full structure is still visible. The evidence of what the universe is. The receding galaxies, the cosmic web, the microwave background, all of it is accessible to us now. It will not be accessible forever. The window is open. We are looking through it. When you point a telescope at the most distant regions of the observable universe and look, you eventually reach something that looks like a wall. Not a wall of matter, a wall of fire. The cosmic microwave background, the CMB, is the oldest light in the universe. It comes from 13.8 billion light-years away, in every direction, arriving from all sides simultaneously. It represents a moment 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, and light to travel freely for the first time. Before that moment, the universe was an opaque plasma, a fog of ionized hydrogen and helium so dense that photons could not travel more than a tiny distance before being absorbed and re-emitted. The universe was a hot, glowing, impenetrable wall in every direction. No telescope could see through it, because there was no light that had traveled through it. All the light had been scattered into uniformity. At 380,000 years, the temperature dropped to about 3,000 degrees. Electrons bound to nuclei. Atoms formed. The universe became transparent. The photons that had been trapped in the plasma were released and streamed outward in every direction. They've been traveling ever since, for 13.8 billion years. The expansion of space has stretched them from visible light to microwaves. Today they arrive at our antennas and satellite dishes as a faint microwave glow, uniform in every direction. Temperature 2.725 degrees above absolute zero. This is the CMB, the farthest thing we can see, the edge of our visibility. Everything before 380,000 years after the Big Bang is behind that wall of ancient fire and light. Not because that era doesn't exist in the historical record. It does, encoded in the structure of what came after. But because there is no light from that era that has traveled to us intact. The universe was opaque. Everything that happened before recombination is hidden. This is not the edge of the universe. This is the edge of what we can see with light. It's a temporal boundary, not a spatial one. The universe extended beyond that surface in 380,000 AD, just as it extends beyond our visible sphere today. The CMB is the most distant surface from which light can reach us, but space exists beyond it. Both in the spatial sense, the universe extends further than 46 billion light-years, and in the temporal sense, the universe existed before 380,000 years after the Big Bang. We simply can't see that era with photons. What was beyond the wall 380,000 years after the Big Bang? The same opaque plasma, extending in all directions, filling all of space. What's beyond the CMB right now, in spatial terms? More universe, more galaxies, stars, planets, expanding space. The same universe, but further away than light has had time to travel to us. Let's address the explanation you've probably heard, because getting it right changes everything. The most common explanation of the expanding universe uses a balloon. Imagine the universe is like the surface of a balloon. Galaxies are dots on the surface. When you inflate the balloon, all the dots move apart from each other. No dot is at the center of the expansion. No dot is at the edge. The expansion is happening everywhere on the surface, simultaneously. This analogy is genuinely useful. It correctly captures several real features of the expansion. It shows why every galaxy sees every other galaxy receding, because the surface is expanding everywhere, not because galaxies are moving through space. It shows why there is no center of expansion. Every point on the surface sees the same recession of neighboring points. It shows why more distant galaxies recede faster. They're further along the surface, and more surface is being created between you and them. These are correct features of the actual universe. But the analogy does one thing that is catastrophically misleading, and almost every explanation fails to acknowledge it. The balloon exists inside a room. When you inflate the balloon, it expands into the three-dimensional space of the room. The room is the container. The balloon is the thing inside it. And immediately, without being told to, your brain asks, what's the room? What is the three-dimensional space that the universe balloon is expanding into? The answer is, there is no room. The analogy requires one. Reality doesn't have one. The balloon analogy is a two-dimensional surface expanding in three-dimensional space, used to represent a three-dimensional space expanding in nothing. There is no fourth spatial dimension that our three-dimensional space is expanding into. No higher dimensional room. No container. No outside. The expansion of the universe is not the expansion of something inside a container. It is the expansion of the container itself, if there is no container. It is space getting bigger, where space is all there is and there is nothing for it to expand into. This is genuinely difficult to picture. It is difficult because every physical analogy you can draw involves something inside a larger space. There are no everyday examples of a space expanding without being inside something larger. The concept exists in the mathematics of differential geometry. It is called intrinsic curvature, and it means a space can have geometry without being embedded in a higher dimensional space. But it has no everyday equivalent. No object you have ever seen demonstrates it. So the honest answer to what is the universe expanding into is this. Nothing. Not empty space. Not a void. Nothing. The expansion of space does not require an outside, and there is no evidence that an outside exists. Space expands as a property of space itself, not as movement through something else. And the honest answer to what's beyond the edge is, the edge may not exist. The universe, based on what we can measure, extends infinitely. It has no boundary in any direction. There is no wall, no outside, no surrounding medium, no container. The universe is not inside something else. It just is. When you map the universe at microwave wavelengths, you find something that looks like a wall, a uniform glow coming from every direction in the sky at the same temperature, surrounding us completely. This is the cosmic microwave background, the oldest light in the universe. And it is not the edge of space, it is the edge of our vision, which is a very different thing. To understand what the CMB is, you have to understand what the universe was before it. For the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. An ionized gas so hot that electrons couldn't stay bound to atomic nuclei. They moved freely through the hydrogen and helium. And free electrons do something specific to photons. They scatter them, constantly. A photon produced in the early universe couldn't travel more than a short distance before hitting an electron and being deflected in a new direction. The universe was brilliantly luminous, but completely opaque, a glowing fog through which light could not escape. Any photon that existed in those first 380,000 years was trapped, bouncing from electron to electron, going nowhere. The universe burned with light, and the light went nowhere. At 380,000 years, something changed. The temperature dropped to about 3,000 degrees Kelvin. Hot, but cool enough that electrons could bind to nuclei. Hydrogen atoms formed. Helium atoms formed. With electrons no longer free, photons suddenly had nothing to scatter off. The plasma became a neutral gas. The universe became transparent. In that moment, all the light that had been trapped in the plasma was released. It streamed outward in every direction through the newly transparent universe. Those photons have been traveling ever since. 13.8 billion years. The expansion of space has stretched their wavelengths from visible light to microwaves. They arrive today from every direction as the CMB, a faint, uniform microwave glow at 2.725 degrees above absolute zero. This is the edge of what we can see with light. The surface of last scattering. The moment when the universe first became visible. But here is what it is not. The CMB is not the edge of the universe. It is not a surface beyond which there is nothing. Beyond the CMB surface, in every direction, is more universe, more space, more matter. The same continuous space that surrounds us, populated by more galaxies and more stars, extending outward beyond the limit of our vision. We cannot see beyond the CMB, not because there is nothing there, but because the universe was opaque before 380,000 years. Any light from before that era was scattered and thermalized, absorbed into the plasma's heat bath, and re-emitted as part of the CMB itself. The early universe erased its own light record. Whatever happened before recombination left no directly observable photons for us to detect. This means everything before 380,000 years is, for photon-based astronomy, hidden, not gone, not non-existent. Hidden. The Big Bang, inflation, the first moments of nucleosynthesis. We know they happened from indirect evidence, from the structure of what they produced. But we cannot see them directly with any telescope that detects light. The CMB is the universe's baby photograph, its earliest visible face. And behind that face, earlier in time, further in space, is a universe we cannot observe directly, but that exists, extending outward in every direction, further than any measurement we can make. The wall of ancient fire is not the edge of space. It is the limit of our vision. The balloon analogy has probably been used to explain the expanding universe to you at some point. Galaxies are dots on the surface of a balloon. Inflate the balloon, and all the dots move apart. No dot is at the center. No dot is at the edge. This analogy correctly captures something important. It shows why every galaxy sees every other galaxy receding. Because the surface is expanding everywhere, simultaneously. Not because galaxies are moving through space in an absolute sense. It shows why there's no center of expansion. It shows why more distant galaxies recede faster. More surface is created between dots that are further apart. These are real features of the actual universe. But the balloon analogy has a flaw that almost every explanation ignores. And the flaw is specifically the one that matters for the question of what's beyond the edge. When you inflate a balloon, the surface expands into the three-dimensional space of the room around it. The room is real. The balloon is inside the room. The room is the larger space that the balloon universe is expanding into. And your brain, hearing the analogy, immediately asks, what is the room? The answer is, there is no room. The balloon analogy represents a three-dimensional universe using a two-dimensional surface. The two-dimensional surface expands in three-dimensional space. But our three-dimensional universe does not expand in a four-dimensional space. There is no fourth spatial dimension that our universe is expanding into. No surrounding void. No container. No room. The expansion of the universe is not the expansion of something inside a larger space. It is the expansion of space itself, where space is all there is. Space gets bigger. There is nothing for it to expand into. The expansion is a property of the geometry of space-time, not a motion through something else. This is genuinely hard to picture. Every analogy you can draw involves something inside a larger space, because everything you've ever encountered is inside a larger space. The universe is the only thing that isn't. There is no analogy for it that doesn't require something that works like a room. So the honest explanation is, the balloon analogy gives you the right picture of what happens on the surface. It gives you the wrong picture of what the surface is inside of. Because the universe isn't inside anything. It is the inside. Here is the clearest way to understand why what's outside the universe might not be a meaningful question. Go to the North Pole. Stand there. Face any direction. Every direction you can face is south. You can walk in any direction, and you'll be moving south. There is no north from the North Pole. North is a direction that exists on the surface of a sphere. At the pole, the direction north ceases to apply. If someone asks, what's north of the North Pole? The question has no answer. Not because no one has looked. Not because the north is very far away. Because north, as a direction, does not exist at that specific geometric point. The question assumes that north exists as a direction from every point on the sphere. That assumption is false at the pole. The universe is a similar case for the concept of outside. Outside is a spatial concept. When you say something is outside something else, you mean it occupies a region of space beyond the boundary of the first thing. But the universe is all of space. There is no region of space beyond the universe, because space is what the universe is made of. Asking what's outside the universe uses the very thing it's asking about, space, as a prerequisite for the question to make sense. Without space, outside has no meaning. Without an outside, the universe has nothing to be outside of. This is not a dodge. It is not a way of saying, we give up. It is a specific logical observation about what the question requires versus what the universe actually is. The question, what's outside the universe, assumes there is a space surrounding the universe. If the universe is all of space, this assumption is false. The question is grammatically correct, but physically malformed. Like, what's north of the North Pole? It sounds like it should have an answer. It doesn't, because the concept it applies doesn't apply here. Let me try a different approach to the same idea. Stand at the North Pole of the Earth. Look around. You're standing on a sphere, and every direction from where you're standing is south. You can walk in any direction, and you'll be moving away from the pole, moving south. Now someone asks you, what's north of where you're standing? The question has no answer, not because you don't know, not because it's very far away, because north is a direction defined on the surface of a sphere, and at the North Pole, the direction north doesn't exist. Every direction from that point is south. The concept of north has no application at the North Pole. This is not a failure of language or knowledge. It's a fact about the geometry of spheres. At the pole, one direction simply ceases to apply. Stephen Hawking used this analogy to address the question of what came before the Big Bang, but it applies equally to the question of what's outside the universe. Just as the North Pole has no north, the universe may have no outside. Not because the outside is hidden. Not because we can't reach it. Because the concept of outside the universe is like north of the North Pole. The universe is the context in which the word outside has meaning. Asking what's outside the universe is asking for an outside to the thing that defines what outside means. It is not a question without an answer that we haven't found yet. It may be a question that asks for something, that does not exist. The Planck satellite, launched by the European Space Agency in 2009, mapped the cosmic microwave background in greater detail than any previous instrument. The CMB contains information about the geometry of the universe, encoded in the statistical properties of its temperature fluctuations. Here is why. Sound waves were propagating through the early universe's plasma before recombination, driven by the interplay of gravity and radiation pressure. These sound waves left a characteristic pattern of density fluctuations, overdense and underdense regions, imprinted on the plasma at the moment of recombination. Those fluctuations, frozen into the CMB, tell us about the geometry of the space they crossed. In a positively curved universe, the angular size of those fluctuation patterns on the sky would appear larger than in a flat universe, because space curves like a lens. In a negatively curved universe, they'd appear smaller. In a flat universe, the angular size matches the theoretical prediction exactly. The Planck measurements found an angular scale consistent with a flat universe, consistent with no curvature, to a precision better than 1%. The most precise measurement ever made of the universe's geometry is flat. This does not definitively prove infinite extent. It is possible that the universe is very slightly positively curved, but the curvature is too small to detect with current instruments. In that case, the universe would be finite, but so large that its curvature is invisible to us. The way Earth's curvature is invisible to someone standing on the surface looking at a small area. Such a universe would be many times larger than the observable universe, but would still eventually close back on itself. But the honest statement of what the evidence says is, the universe's geometry is consistent with being flat and infinite. The flat infinite option is the one best supported by current data. A flat, infinite universe has no edge. Let's come back to where you are right now. You're in a room, or a bed, or some specific location on the surface of a small rocky planet orbiting a medium-sized star in the outer arm of a barred spiral galaxy containing about 300 billion stars. Sitting in a local group of a few dozen galaxies, sitting in a supercluster called Laniakea, sitting in a cosmic web of filaments and voids, sitting in an observable universe 46 billion light-years in radius, containing 2 trillion galaxies. And outside that observable universe, in every direction, is almost certainly more universe, more galaxies, more stars, more planets, more space, possibly infinite more. The same physics, the same laws, the same kinds of structures, and the boundary between what you can see and what you can't is not a wall. It's a time limit. Light hasn't had time to travel from beyond 46 billion light-years to reach you yet. That's the only reason for the boundary. There is no physical edge, no wall, no transition from universe to non-universe. Just space, and the limit of how far light has traveled in 13.8 billion years of cosmic history. Beyond what you can see is more of what you can see. And then beyond that is more. And beyond that, possibly, more forever. The universe does not end the way a room ends. It does not end the way a map ends. It may not end at all. It may simply extend outward, in every direction, without limit, without boundary, without anything on the other side. This means the question, what's beyond the edge, may have no subject. There is no edge. That is either terrifying or beautiful. It is probably both. Dark energy is not doing what you think it's doing. Most descriptions of dark energy say it is causing the universe to expand. This is true, but imprecise in a way that matters. The expansion of the universe was already happening. Dark energy is causing that expansion to accelerate. The galaxies were already moving apart. Dark energy is making them move apart, faster and faster, and faster still, compounding over time, in a process that has no off switch and no end. The difference between expansion and accelerating expansion is the difference between a boat drifting away from shore and a boat whose engine is running, pushing it further and faster every second. The first kind you could theoretically reverse given enough force. The second kind, after long enough, is permanently, irrecoverably gone. Dark energy is the engine, and it has been running for approximately 5 billion years. Here is what it is doing to the specific boundary that matters. Not the edge of the universe, which doesn't appear to exist, but the cosmic event horizon, which does. The horizon is the distance beyond which anything that exists right now can never, under any circumstances, ever send a signal that reaches us. Not slowed by distance. not delayed by a very long journey. Never. Not in infinite time. The galaxies beyond the horizon are not just very far away. They are causally severed from us by the geometry of an accelerating universe. Their light will never reach us. Their existence will never intersect ours in any physical way again. That horizon sits today at approximately 16 billion light-years from Earth. And it is shrinking. Not because the universe is collapsing, not because the expansion is slowing. The horizon is shrinking because the expansion is accelerating. As nearby space expands faster, the shell of space at the horizon distance is being pushed outward faster than the speed of light. Not because anything is moving through space at superluminal velocity, but because space itself is expanding between us and the horizon at an effective rate that exceeds the speed of light. Light, trying to travel toward us from just inside the horizon, has to run against this expansion. It is running a race in which the finish line is moving away, and dark energy is making the finish line move faster. The specific consequence: there are galaxies that we can see tonight, galaxies visible in current telescopes, galaxies that have been photographed and catalogued and studied, that have already crossed the event horizon. Their light, emitted billions of years ago, is still arriving, but new light emitted from those galaxies right now, will never reach us. The images we see of them are the last messages they will ever send. We are watching the final transmission of regions of the universe that are, in the causal sense, that actually matters, already gone. About 10,000 galaxies per year are being lost this way. 10,000 times per year, a galaxy crosses the event horizon, and the last light it will ever send us is already in transit, already the final word, even if it takes another billion years to arrive. We do not notice this. We cannot notice it. Each galaxy's final light looks exactly like all the light that came before it. Only the knowledge that the horizon exists and is contracting reveals what those images actually represent. Follow this forward in time, because the endpoint is specific and strange. 1 trillion years from now, roughly 70 times the current age of the universe, the cosmological picture will be almost unrecognizable from what we see tonight. The Milky Way will have merged with Andromeda. That collision is coming in approximately 4.5 billion years. And the local group of galaxies will have gravitationally contracted into a single merged system. The local group is bound. Its members are gravitationally attached to each other. Dark energy, which operates on the scale of the expanding universe, does not pull them apart, because gravity, at the local scale, is stronger than the cosmological acceleration. The merged local group will remain intact, orbiting its shared center of mass. Stable. But everything outside the local group, every galaxy cluster, every galaxy, every star outside our immediate gravitational neighborhood, will be gone, not destroyed, carried away. The cosmic event horizon will have contracted to the point where the only things inside it are the local group galaxies. The Virgo cluster, visible tonight at 50 million light-years, will have crossed the horizon. The Perseus cluster, the Coma cluster, the Shapley supercluster, all of them gone in the causal sense, their light permanently unable to reach us, not because they died, because space between them and us expanded faster than their light could cross it. The night sky in 1 trillion years, viewed from a planet in the merged local group galaxy, will be radically different from tonight's. Outside the local group, there will be nothing. The galaxy density of the observable universe, 2 trillion galaxies tonight, will be effectively zero. A civilization developing in that era will look at the sky, survey it with the most sophisticated instruments imaginable, and find local stars, local galaxies in the merged local group, and then darkness. Absolute darkness in every direction beyond the local group's edge. They will have no empirical evidence that the universe extends beyond what they can see. Everything else will have been carried behind the horizon. They will not know about the Virgo cluster. They will not know about the cosmic web. They will not know about the 2 trillion galaxies that existed in what we would call the present. If they develop cosmology at all, they will have far less to work with. The critical observations that we use to understand the universe, the distribution of galaxies across cosmic history, the pattern of galaxy clustering, the Hubble constant measured from galaxies at different distances, all of these require objects beyond the local group. In 1 trillion years, there are no such objects within the horizon. A civilization in that era might conclude that their galaxy is the entire universe. not out of arrogance or scientific failure, because every observation would be consistent with it. There would be nothing to indicate otherwise. They would be wrong, but they would have no way to know. This is the specific, underappreciated gift of living now, in this particular moment in cosmic history. We can see 2 trillion galaxies. We can observe the universe's structure across billions of light years of its history, because those galaxies are still within our horizon, and their light is still arriving. We can measure the Hubble constant from the recession speeds of galaxies at different distances. We can observe the CMB, the afterglow of the Big Bang, stretched across the entire sky, carrying encoded information about the conditions of the universe's first moments. We can see the large-scale structure of the cosmic web, the distribution of filaments and voids that traces the universe's evolution from near uniformity at the Big Bang to its current clustered complexity. All of this evidence is available to us right now, and not to the civilizations of the far future, because right now, all of these things are within our horizon. Their light has had time to reach us. Their existence is visible to us. In 1 trillion years, most of this evidence will be gone behind the horizon. The civilizations of that era will inherit a universe that has already erased most of the evidence of its own history and structure. They will have fewer data points. The cosmological questions we can investigate with relative richness. How many galaxies are there? What is the large-scale structure? How fast is the universe expanding? Will be harder or impossible for them to address, not because they are less scientifically capable, but because the observational material will no longer be available. We are, in a specific sense, living at the richest moment for observational cosmology that will ever exist. The universe is old enough to have interesting structure and young enough that most of it is still inside the horizon. This window will close. It is closing right now, galaxy by galaxy, as the horizon contracts. The 2 trillion galaxies visible tonight are a gift of timing. We happen to exist at the right moment to see them. Here is where the question, what's beyond the edge of the universe, takes a turn that is not about space in the ordinary sense. The inflationary model of the early universe, the theory that the universe underwent a period of extraordinarily rapid exponential expansion in the first fractions of a second after the Big Bang, is the leading explanation for several features of the universe that are otherwise difficult to explain. Why is the universe so flat? Why is it so homogeneous? Why does it look the same in every direction, even in regions that were too far apart to ever have been in causal contact? Why do we see the specific pattern of temperature fluctuations in the CMB that we observe? Inflation answers all of these. A brief period of rapid exponential expansion would flatten the geometry, homogenize the temperature, and generate the specific quantum fluctuations that seeded the large-scale structure we observe today. The theory is not confirmed, but it is consistent with every observation we have and has made specific, tested predictions that have held up. The deeper implication of inflation, the one that is less discussed in introductory treatments, is what happens when you ask whether inflation stopped everywhere at the same time. The answer, in the most commonly accepted versions of the theory, is no. Inflation is driven by a hypothetical field, the inflaton field, that was trapped in a high-energy configuration in the early universe. The field eventually decayed, transitioned to its low-energy state, which is what ended inflation and triggered the hot Big Bang we think of as the beginning of the universe. But quantum mechanics introduces uncertainty into this decay. The inflaton field doesn't decay everywhere simultaneously. Different regions decay at different times. Where the field has decayed, inflation ends and a hot Big Bang occurs, producing a universe like ours. But in regions where the field has not yet decayed, inflation continues. The critical mathematical feature of inflation is that the exponential expansion creates new space faster than regions can decay out of it. In the regions still inflating, space is expanding so rapidly that the volume of inflating space is always increasing, even as some patches decay out of it and become universes. The inflating background, the Matorn universe in which our universe is embedded, never exhausts itself. It continues forever, generating new patches that exit into their own hot Big Bangs, each one becoming a universe, isolated from all the others by the inflating background that separates them. This is eternal inflation, not just a long inflation that eventually ends everywhere, an inflation that literally never ends. That continues forever. That continuously generates new bubble universes, including ours, in an endless, exponentially growing background of inflating space. If eternal inflation is correct, then beyond the edge of the universe has an answer in a specific sense. Not spatially beyond, there is no spatial edge to our universe's interior space, but in the higher dimensional sense of what our universe is embedded in, of what the inflating background is, there is more. Other bubble universes, expanding in their own regions of the inflating background. Some of them may be very similar to ours. Some may have different physical constants, different numbers of spatial dimensions, different laws of physics, because the specific physics of a universe is determined by how the inflaton field decays. And different bubble universes may decay differently, producing different physical laws. We cannot see these other bubble universes. We cannot interact with them. They are causally separated from us by the inflating background between our bubble and theirs. A separation not of space, but of the phase transition that ended inflation. Our universe's edge in this sense is not a wall in space. It is a phase transition between where our inflation ended and where it continues or ended differently. The other universes are not behind a spatial wall. They are separated from us by a fundamentally different kind of distance. There may be exceptions, moments where two bubble universes, expanding from their respective nucleation points, expanded into each other. A bubble collision. If two expanding bubble universes collide, the collision would leave an imprint on the CMB of each, a circular anomaly in the temperature pattern, where the physics of the collision region differs from the surrounding unaffected CMB. The CMB cold spot in the direction of the constellation Eridanus has been proposed by some cosmologists as a potential bubble collision signature, though this remains speculative and contested. If we found such a signature, confirmed beyond statistical doubt, it would be direct observational evidence that our universe is one of many, that the inflationary background is real, that beyond our universe is not an empty phrase, but a description of an actual structure. Other bubble universes, expanding in the same inflating background, each one a separate cosmos with potentially different physics. String theory, the framework that attempts to unify quantum mechanics with general relativity, predicts an almost incomprehensible number of possible configurations of space-time at small scales. Each configuration corresponds to a different set of physical constants, a different mass for the electron, a different strength for gravity, a different value for the cosmological constant that drives dark energy. The number of possible configurations in string theory is estimated at 10 to the power of 500. That is a 1, followed by 500 zeros. A number so large that even expressing it requires notation rather than digits. Each of these configurations is, in principle, a possible universe. A universe with slightly different laws of physics, different particle masses, different constants, different cosmological behavior. If eternal inflation continuously generates new bubble universes, and if the physics of each bubble is determined by which of these configurations the inflaton field decays into, then the different bubble universes would have different physics. The string landscape of possible configurations would be sampled across the multiverse of bubble universes. Our universe, with our specific electron mass, our specific gravitational constant, our specific cosmological constant, would be one point in a landscape of 10 to the 500 possible universes. This has a specific and controversial implication for one of the most puzzling questions in physics. Why is our universe's cosmological constant so small? The cosmological constant, the value of dark energy density, is observed to be approximately 10 to the power of negative 122 in natural units. This is an extraordinarily small number, far smaller than any physical calculation of vacuum energy predicts it should be. The discrepancy between the calculated and observed values of the cosmological constant is 120 orders of magnitude, the largest discrepancy between theory and observation in the history of physics. In the landscape of possible universes, there would be universes with larger cosmological constants, many of them. But in a universe with a much larger cosmological constant, dark energy would be so powerful that expansion would overwhelm gravity before any structure, galaxies, stars, planets, could form. No galaxies, no stars, no planets means no life. In a universe with a much smaller cosmological constant, zero or negative expansion would eventually reverse into collapse, again preventing the long-term stability that allows complex structures to develop. The anthropic argument, of all the bubble universes in the multiverse, Only the ones with cosmological constants in the narrow range compatible with the existence of life can be observed by anyone. We are necessarily in a universe where the cosmological constant is small enough for life to exist. Not because there is some deep reason for our universe to have this value, but because only universes with this value are observable from the inside. It's not that our universe is special. It's that we can only exist to ask the question in the specific universes where life is possible. This argument is either profound or profoundly disturbing, depending on your perspective. It explains the cosmological constant without explaining it. It predicts that we would observe a small cosmological constant without identifying any mechanism that produces small values. It is explanation by selection rather than explanation by physics. Some physicists find this deeply unsatisfying. Others find it the only consistent response to an observation that no other framework explains. What it implies for the question of what's beyond the edge is this: if the multiverse is real, then there is genuinely something beyond our universe. Not spatially beyond, not something on the other side of a wall, but in the deeper sense of other regions of the inflationary background where other universes exist, with different physics, different constants, possibly different numbers of dimensions. Our universe is one possibility in a space of possibilities. The space of possibilities is real. Its other points are real universes, even if we can never reach them or communicate with them. The beyond is real. It's just not spatial. It is the landscape of all possible physics, and our universe occupies one location in it. In 2008, a team of cosmologists, led by Alexander Kashlinsky, published a paper reporting an anomalous motion in a large sample of galaxy clusters. The clusters appeared to be moving, collectively, in a specific direction on the sky, toward the constellation Centaurus, at velocities not accounted for by the local gravitational environment, the distribution of matter in the observable universe. This coherent bulk flow, dubbed dark flow by the researchers, was puzzling because the standard model of cosmology predicts that on sufficiently large scales, the universe should be homogeneous. The gravitational influence of structure within the observable universe should average out. There should be no preferred direction of motion on the scale these researchers were observing. But if something beyond the observable universe, a massive concentration of matter, or some other large-scale structure that existed in the universe before inflation smoothed everything out, now beyond the horizon, we're exerting a gravitational pull on our entire observable volume, it could produce exactly this kind of coherent motion. Everything inside our horizon would be gravitationally attracted to this external mass, creating a bulk flow in its direction. The dark flow is contested. Subsequent analyses of the same data and of new datasets have produced inconsistent results. Some analyses reproduce the signal. Others find no statistically significant bulk flow above what the standard model predicts. The scientific status of dark flow is unresolved. It is neither confirmed nor definitively ruled out. But the concept it introduced, that something beyond the cosmic horizon could be affecting the observable universe, is physically legitimate. The horizon is a causal limit, not an absolute isolation. Gravity, in general relativity, is not transmitted by signals but by the geometry of spacetime. A massive structure beyond our horizon could have imprinted its gravitational influence on our region during the inflationary epoch, when our observable volume was causally connected to much larger regions of space. The inflation that followed would have preserved this imprint, even as it stretched the regions beyond our horizon out of causal contact. This means that the observable universe is not necessarily self-contained in terms of its gravitational environment. The distribution of matter inside our horizon may have been shaped, in the distant past, by structures that are now beyond the horizon. What we see as the statistical properties of the CMB fluctuations, the specific distribution of hot and cold spots, may carry the fingerprints of regions of space we can never see. The horizon is not a wall in space, but it is the edge of what we can observe, and what lies beyond it may not be completely irrelevant to what we observe inside it. The cosmic microwave background is the most precisely characterized natural radiation field in all of physics. It is not perfectly smooth. It contains temperature fluctuations at the level of 1 part in 100,000, tiny variations in intensity from one direction to another, that carry encoded information about the conditions of the early universe. The standard inflationary model predicts the statistical properties of these fluctuations with extraordinary precision, and the agreement between prediction and observation is remarkable. a triumph of the combination of general relativity, quantum field theory, and observational cosmology. But there are anomalies, not dramatic violations of the standard model. Subtle statistical departures from the predictions that, depending on how you analyze the data, appear to be there. The most discussed are the large-scale anomalies. At the very largest angular scales on the sky, the modes whose wavelengths are comparable to the diameter of the observable universe. The power spectrum of CMB fluctuations is lower than the standard model predicts. There is less power on the largest scales than there should be. This is sometimes called the low quadrupole or power deficit anomaly. At the same large angular scales, there is a specific pattern sometimes called the axis of evil. The largest scale fluctuations in the CMB appear to be aligned with each other, and aligned with the direction of the solar system's motion, in a way that is statistically unlikely if the universe is truly isotropic. Different large-scale modes of the CMB fluctuations, which in a random universe should have independent orientations, appear to share a common preferred direction. There is also the cold spot, a region of anomalously low CMB temperature in the direction of the constellation Eridanus. Much colder and much larger than statistical fluctuations of the standard model predict. Various explanations have been proposed. A supervoid, a region of below-average matter density that has produced a temperature decrement through the integrated Sachs-Wolf effect. A primordial fluctuation from inflation that happens to be large, or the bubble collision signature mentioned earlier. Each anomaly individually can be explained as a statistical fluctuation, unlikely but not impossible in a finite universe. What makes them collectively interesting is the combination, several independent anomalies, all at the largest scales, all pointing to something potentially different about the structure of the universe at scales comparable to or larger than our observable volume. One possible explanation. If the universe were finite, if it is actually a very large but bounded space, perhaps much larger than the observable volume but not infinite, then the largest scale modes of CMB fluctuations would be affected. In a finite universe, certain wavelengths of fluctuation cannot exist, the same way a finite box can only contain standing waves with specific wavelengths. If the universe's size is not much larger than the observable volume, these constraints would show up as a suppression of large-scale power, and potentially as preferred directions. Exactly the anomalies we observe. A finite universe would be consistent with positive curvature, a slight bending of space-time that eventually closes back on itself, like the surface of a sphere but in 3 dimensions. The Planck measurement constrains this to be no more than 0.4% deviation from flat. A universe with a barely detectable positive curvature could be finite, but so large that its circumference is hundreds of times the diameter of the observable volume. We would be living in a vast but bounded cosmos, seeing only a small fraction of it, with the CMB fluctuations carrying the faint statistical signature of the boundaries we cannot directly observe. The anomalies are not proof of this. They are hints. The data is consistent with multiple explanations, and no single explanation has achieved scientific consensus. But the pattern is there. At the largest scales, the scales closest to and potentially extending beyond the horizon, something is different. Let's be precise about what outside the universe would even mean, because this is where the conversation usually becomes either comfortable or completely dishonest. Outside is a spatial concept. When you say that an object is outside a container, you mean it occupies a region of space that is not within the container's boundaries. The concept of outside requires that space exists both inside the container and outside it. The container is a subset of a larger space, and outside refers to the complementary subset. Now apply this to the universe. The universe is, by definition, all of space, not a subset of a larger space, all of it. If the universe is all of space, then there is no space outside the universe, because all space is the universe. Asking what is outside the universe is asking about a region of space that is not part of the universe, but the universe is all space. So there is no such region. This is not a rhetorical trick. It is the logical consequence of what universe means. But there is a potential escape from this argument, and it is where the conversation becomes genuinely deep. When cosmologists talk about the multiverse, or about the inflating background in which our bubble universe nucleated, they are implicitly extending the definition of space. Our universe is space, the space we can observe, the space that is curved and expanding, and containing 2 trillion galaxies. is not the only possible kind of spatial existence. The inflating background is a different kind of space-time, one with different geometry, different energy density, different causal structure than our universe's interior. In this framework, outside the universe refers to a different region of space-time, not a region of our universe's space that we cannot reach, but a qualitatively different space-time that is not part of our universe's interior. The inflating background, in this picture, is not nothing. It is something. It is a space-time structure of its own, with its own geometry, in which our bubble universe is embedded. This does give meaningful content to the phrase, outside the universe. But it is not the outside that the intuitive question is asking about. The intuitive question imagines ordinary space extending beyond the universe's edge, the same kind of space we live in, just on the other side of the wall. What the multiverse framework offers instead is a qualitatively different kind of existence that underlies our universe, in which our universe is embedded and from which our universe nucleated. It is less like asking, what's on the other side of the wall, and more like asking, what is the wall made of? The answer turns out to be something real, something physical, something that has causal influence on what happens inside our universe, but not the ordinary space that the intuitive question was looking for. The intuition was right, that there is something there. It was wrong about what kind of there it is. The question cosmology cannot answer. And why that matters. There is a point at which physics stops. Not in the colloquial sense of, we haven't figured it out yet, but in the technical sense of what a physical theory can in principle address. A physical theory is a mathematical structure that makes predictions about observable quantities. The predictions are tested against observations. The theory's domain is bounded by what is, in principle, observable, by what can send a signal to an observer. The cosmic event horizon marks the boundary of what can send a signal to us. Objects beyond the horizon cannot, even in principle, affect any observation we make. They are causally disconnected from us. A physical theory about our universe, a theory whose predictions can be tested against our observations, has no obligation to say anything about what's beyond the horizon. What's beyond the horizon is outside the theory's domain. This is a specific and precise claim. Not, we don't know what's beyond the horizon. We cannot, even in principle, gain observational access to what's beyond the horizon. Any theory about what's there is untestable by definition. It may be compelling. It may be mathematically consistent. It may be the most parsimonious extension of well-tested physics, but it cannot be empirically tested, which means it occupies a different epistemic status from ordinary scientific claims. The multiverse, if real, is not, in the normal sense, a scientific theory. It is a consequence of well-tested theories, inflation, quantum field theory, extended into domains beyond observation. The extension may be correct, but the extension cannot be confirmed by any conceivable experiment. This is where the conversation about what's beyond the edge of the universe reaches its honest conclusion. Not, we don't know yet. Not, give us better instruments and we'll find out. The honest conclusion is, beyond the horizon, physics is making its best extrapolation. It is taking the well-tested physics of the observable universe and projecting it outward. Those projections are not arbitrary. They follow from rigorous mathematics and well-confirmed theory. But they are projections, not observations. They are the furthest reach of scientific inference, extended into territory it can characterize, but never verify. The universe has a hard edge, not a spatial edge, but an epistemic one. The horizon is the edge of what physical theory can in principle test. Beyond it, the universe is described by projection and extrapolation. The map has a border, not because territory ends there, but because the surveyor cannot cross. This is not a failure. It is the honest acknowledgement of what a physical theory is. A theory of everything is not a God's eye view of all possible existence. It is the best description of observable reality that physics can construct. The observable is finite. The theory's certain reach is finite. What lies beyond is the domain of inference and mathematics rather than of test and confirmation. And there is something important about that. The limit of what physics can know is not an arbitrary ignorance. It is a structural feature of what it means to be an observer in a space-time with an event horizon. We are inside the universe, not outside it. We can only receive signals from our past light cone, The universe does not extend its knowability to us beyond that limit. This is a hard truth, and it is one that the question, what's beyond the edge, eventually bottoms out on, if you follow it far enough. Come back to tonight. You are in a room, on a planet, orbiting a star, in a galaxy, inside a local group, inside a filament, inside the observable universe. Outside the observable universe, in every direction, there is almost certainly more universe, more galaxies, more space, possibly infinite more, extending forever. The boundary between what you can see and what you cannot is not a wall. It is the limit of how far light has traveled in 13.8 billion years. It will move outward slightly as time passes, as more light from slightly more distant sources arrives. But the expansion-driven acceleration means the horizon, the boundary of what can ever reach us, is shrinking in the other direction, and the net effect is an ever-contracting sphere of physical relevance. The universe of tonight is the largest observable universe that will ever exist, in one sense. The number of galaxies within our horizon will only decrease from here. The evidence available for cosmological inquiry will only diminish. The number of photons we receive from external sources will decrease over trillions of years, toward effectively zero. We are at the most observationally rich moment in cosmic history, and we are watching it pass. Beyond the observable universe, the same space almost certainly continues. In that space, the same physics, or possibly different physics in regions where different quantum vacua are realized, produces the same kinds of structures. Galaxies, stars, planets, possibly life, possibly minds, possibly questions. The same questions. Minds in distant regions of an infinite universe, inside their own observable spheres, asking what's beyond their edge. And the answer is the same for them. Probably more universe, probably the same, possibly infinite. And beyond that, possibly the inflating background, the multiverse, the landscape of possible physics. Or possibly nothing of the sort, possibly a universe that is simply large and flat and infinite, with no embedding structure. Just space extending outward forever in every direction without any outside that could even be conceptualized. There is no wall. There is only more, and you are inside it. Finite, bounded, temporary, standing at the surface of a small blue planet and pointing instruments at the sky, trying to understand what you are inside of. The difficulty of that is not a failure. The difficulty is what it actually feels like to be a finite mind encountering a possibly infinite cosmos. The resistance you feel, the persistent sense that there must be an edge, an outside, something on the other side, is not confusion. It is the honest response of a mind built for bounded spaces trying to hold something genuinely unbounded. You will not resolve this tonight. Nobody has. The best physics we have says flat, infinite, no edge, no outside in any ordinary spatial sense, possibly embedded in something we cannot observe, possibly just extending forever without embedding structure, possibly finite, but far too large to detect the finitude. Each of these possibilities is strange. Each of them has consequences that are difficult to fully absorb. None of them gives you the comfortable answer, the wall with something on the other side, that the intuition was looking for. What they give you instead is something harder and more honest. A universe that does not conform to the expectations of minds that evolved inside rooms and coastlines and atmospheres. A universe that is, in the most careful scientific language we have, probably infinite, possibly embedded, definitely expanding faster than light in its outermost reaches, already carrying galaxies beyond the horizon tonight, reducing the observable universe to its final gravitationally bound remnant over trillion-year timescales, and consistent, precisely consistent, to the limit of measurement, with a geometry that has no edge at all. Here is a consequence of an infinite universe that almost nobody discusses, and it is genuinely uncomfortable in ways that go deeper than the already uncomfortable infinite copies problem. In an infinite universe, standard probability theory breaks down. Probability, as we normally use it, works by counting outcomes in a finite sample space. If you flip a coin, there are two possible outcomes. Heads has probability 1/2, because it occurs in one of two equally likely possibilities. The fraction is well defined because the numerator and denominator are both finite. In an infinite universe, everything that can happen does happen, infinitely many times. There are infinitely many regions where you made a different choice this morning. Infinitely many where you made the same choice. Infinitely many Earths. Infinitely many of every outcome of every quantum event that has ever occurred. Now, try to compute the probability of any specific observation. You want to know, what is the probability that I observe the universe to have the specific properties I measure? In a finite universe, you compare the number of universes with those properties to the total number of universes. But in an infinite universe, both the numerator and denominator are infinite. The probability is infinity divided by infinity, which is undefined. This is called the measure problem in cosmology, and it is one of the deepest unresolved issues in theoretical physics. In an eternal inflationary multiverse, in a framework where infinitely many universes exist, there is no well-defined way to say that one type of universe is more probable than another, because every type occurs infinitely many times. This matters for our earlier discussion of the cosmological constant. The anthropic argument says, we observe a small cosmological constant because only universes with small cosmological constants permit observers. But this argument implicitly assumes that we can compare the probability of different types of universes. That we can say, universes with small cosmological constants, conditioned on having observers, are more probable than universes without observers. In an infinite multiverse, this comparison is not well defined unless you introduce a specific measure, a way of assigning weights to different regions of the infinite space. Different choices of measure give different predictions. Some measures favor our type of universe. Others predict that typical observers in the multiverse should see something very different from what we see. The fact that we see what we see is either evidence for the correct measure or evidence that the multiverse framework is wrong. There is no consensus on which measure is correct. There is not even consensus on what the right criteria for a correct measure would be. The measure problem is not a peripheral technical issue. It is the central obstacle to making the multiverse idea scientifically predictive. What this means for the question, what's beyond the edge, is specific. If the answer involves an infinite multiverse, then the framework that provides that answer also introduces a problem that may be unfixable within existing mathematics. The beyond that eternal inflation offers comes with a cost, the loss of a well-defined notion of probability, which is the foundation of all scientific prediction. The universe may be offering us a beyond and requiring us to give up something fundamental in exchange for it. Flatness does not uniquely determine shape. This is a subtlety that most introductions to cosmological geometry skip, but it changes what no edge actually means. A flat space can have different topologies, different global shapes that all have the same local geometry. On a two-dimensional surface, a flat torus is a good example. Take a square piece of paper, identify the left edge with the right edge, glue them together. Then, identify the top edge with the bottom edge. Glue those together too. The result is a torus, a donut shape. The surface of the torus has a specific curvature. But in the specific case of a flat torus, the square paper can be wrapped around a torus in a way that preserves flatness locally. Walk in any direction on a flat torus, and space has zero curvature everywhere. But travel far enough in one direction, and you return to where you started. A flat torus has no edge, no wall, no boundary, but it is finite. You can circumnavigate it. The same principle applies in 3 dimensions. A 3-dimensional flat space can have the topology of a 3 torus, a cube with opposite faces identified, so that walking through one face brings you out the other. Locally, this space is exactly flat Euclidean geometry. Globally, it is finite and closed with no boundary. In such a universe, the observable universe, our 46 billion light-year sphere, might show specific signatures. If the universe's circumference is smaller than about twice the diameter of the observable sphere, we would see multiple images of the same distant galaxies in different directions. The same galaxy would appear in one direction as it was 5 billion years ago, and in another direction as it was 7 billion years ago, depending on the path the light took to reach us. This Hall of Mirrors effect would produce specific patterns in the CMB, a correlation between fluctuations on opposite sides of the sky that reflects the repeating topology. Searches for this Hall of Mirrors signature in the CMB have been conducted and have not found it. The absence constrains the universe's topology. If the universe is a 3 torus, its circumference must be larger than the observable sphere. This doesn't rule out a topological universe. Just means that if the topology is non-trivial, the repeat pattern is outside our observable volume, and therefore invisible to us. This is the specific frustration of cosmological observations. The constraints we can place are always bounded by the horizon. Anything larger than the observable sphere is inaccessible. The universe could have any global topology that leaves its local geometry consistent with our measurements. We can rule out small topologies. We cannot rule out large ones. The universe might be finite and have no edge, no wall, no boundary, but still have a circumference. A circumference so much larger than the observable sphere that we can never detect it, but finite nonetheless. In such a universe, what's beyond the edge would have no subject. There would be no edge, but how large is the universe would have a finite answer. Just one we cannot measure. There is a specific subtlety in how we interpret cosmological observations that rarely gets stated plainly, and it changes the confidence with which any conclusion can be drawn. We cannot observe a random sample of possible universes. We can only observe our own. And our own observation is not a random sample even of observable universes. It is selected for the specific property that it contains observers. This is the anthropic filter. The observations we make about the universe are necessarily filtered through the fact that we exist. To make them, this sounds abstract. The specific consequence is not. If the universe's parameters had been only slightly different, if the cosmological constant was slightly larger, if the ratio of matter to antimatter from the Big Bang was slightly different, if the initial density fluctuations that seeded galaxy formation were slightly smaller, the universe would not contain galaxies, or stars, or planets, or life. We would not be here to observe. Every observation we make is evidence that the universe's parameters are within the range compatible with our existence, because only observations made from within that range are possible. This means that any fine-tuning of the universe's parameters we observe cannot be treated as random. The parameters are not randomly sampled from a distribution and then observed to be in a particular range. They are selected by the filter of our existence to be in the range compatible with our observation. What appears to be a remarkable coincidence, that the universe has parameters precisely in the narrow range that permits complex chemistry and life, may be no coincidence at all. It is a selection effect. The problem is that this reasoning, applied to the question of what's beyond the horizon, creates a specific epistemic trap. We cannot trust our intuitions about how typical our universe is, because our very existence is selected for an atypical universe. We cannot reason about what most universes look like from the evidence of our own, because our universe is not typical. It is the kind of universe that supports observers, which is an unusual constraint. This is the anthropic shadow, the region of cosmological possibility. Let's make this concrete one more time before tonight ends, because the abstract is easier to forget than the specific. Right now, as you read these words, there are galaxies crossing the cosmic event horizon. Not one at a time, not at some slow background rate that barely registers. 10,000 galaxies per year. On average, sliding past the causal boundary that separates what can ever reach us from what cannot. Each of those galaxies contains hundreds of billions of stars. Some of those stars have planets. Some of those planets, if the physics of abiogenesis is at all general, have life. Some of that life, if the trajectory of complexity on our own planet is any indication, may have intelligence, may have science, may have built instruments and pointed them at the sky and noticed the expansion of the universe and realized, as our cosmologists have realized, that the horizon exists and is contracting, and that the space beyond it is permanently beyond reach. Right now, somewhere in those 10,000 galaxies crossing the horizon this year, there may be a mind, a consciousness, an intelligence with its own specific history and its own specific questions, for whom this is the last year that a signal from our galaxy could, in principle, reach them. The light we emit tonight, traveling in their direction, will be the last light from our region of the universe that can ever reach them. Next year, it will be too late. The horizon will have closed. This is not a distant abstract future event. This is the present. This is tonight. The recession of galaxies beyond the causal boundary is ongoing, continuous, and currently happening. The universe is not contracting. It is not in danger. It is doing what it has been doing since dark energy began to dominate 5 billion years ago. Expanding, accelerating, carrying the most distant structures of the observable universe beyond the edge of causal contact, quietly and without announcement. 10,000 galaxies per year. And it will continue for 1 trillion years, until everything outside the local group is gone from our horizon. Until the only light remaining is from the merged remnant of the local group's galaxies, aging and dimming and cooling in the increasing darkness. This is the future the universe is building, one galaxy at a time, beginning tonight. There is no war, there is only more universe. In every direction, probably infinite, possibly embedded in a larger structure we cannot observe, definitely expanding faster than light at its outermost reaches, carrying the most distant galaxies beyond the horizon now. And you are inside it, not outside it looking in, not at the edge of it looking out. In the middle, in the specific room you occupy, at the specific moment you are in, inside the most observationally rich period of cosmic history that will ever exist. The 2 trillion galaxies are still within the horizon. The evidence is still arriving. The question is still answerable to the degree that it is answerable at all. Ask it now. Think it now, while the universe is still showing you everything it has. Tell us in the comments where on this planet you're listening from tonight. Your city, your country, wherever you are right now. We want to know. If tonight gave you something real to carry into sleep, like the video, and subscribe to Calm Theory for sleep. Sleep well. You are inside something that may have no outside. And tonight, all of it is still here. Why? That we systematically cannot observe because our existence is incompatible with what exists there. Beyond the shadow lies the space of possible universes in which no observers form, and no one asks what's beyond the edge. The shadow is invisible to us, by definition. Its contents are, in principle, unknowable from within the kind of universe we inhabit. It introduces a specific humility about all cosmological reasoning. The universe we inhabit, and our observations of it, are not a neutral sample. They are a biased sample from a distribution we cannot directly access. This does not make cosmology impossible. It makes it necessary to be careful about when the anthropic filter is and is not distorting the inference.